Hello everyone, thank you for joining with my poster. My poster title is Do Archean Cratons Impact the Initiation of Subduction? In the first slide, I'll give an introduction. So cratons are the stable parts of the Earth continental crust and that have remained greater than 2.5 billion years. Geological observations and the numerical studies suggest that these cratons can change the mantle convection pattern, cooling rates, as well as tectonic settings on early Earth. However, our understanding of the impact of the cratons on mantle convection is far from complete. Therefore, in this study, we investigate the influence of the craton formation on mantle convection and the early Earth tectonics. We used two different parameters in this study to identify its impact: cratonic coverage and the cratonic growth rates. But in this poster, I will go through the first parameter, that is cratonic coverage. Cratonic coverage is the surface area of the craton with respect to the whole Earth surface area. The second slide, I'm explaining my methodology. So we use the numerical geodynamic modeling approach. Underworld zoo software is used. And in the model, we solve the mass conservation equation, Stokes equation, and energy conservation equation. Diffusion creep rheology is used, and the crustal weakening is done by pseudoplasticity. Density is temperature dependent. Partial melting is implemented following CISO at 2015. And these are the table shows the physical properties of the model. The yield strength value of the craton is 100 times higher than the yield strength value of the oceanic lithosphere, and we use that value following Lenardic 2003 modeling work. So in the third slide, we are looking at the initial setup and the evolution of the reference model. The first diagram shows the initial viscosity profile, and viscosity is temperature dependent, and initial thermal profile is illustrated in figure A. So we allow the model to run for few billion years and let the stable thermal convective cells to form in the model. After stable cells are formed, we introduce two cratonic segments to the model. That's what we are looking at the figure B here in the figure 1. So these cratonic segments contain cratonic seat, cratonic crust, and cratonic roots. The figure C illustrates the cratonic growth of the model. We introduce the lateral cratonic growth as well as vertical cratonic growth. The lower boundary of the cratonic root can reach 250 kilometers, and lower boundary of the cratonic crust can reach 60 kilometers depth. The lateral growth depends on the cratonic coverage and the growth rates. The cratonic coverage is parameterized, and we give the values of 0, 70%, 35%, 46, likewise up to 78%. We use these values as homogeneous as possible, but because of the challenges in the numerical modeling and parallel running, we could reach these set of values for the cratonic coverage. And then we measure the surface heat flow, Nusselt number, and the average mantle temperature in the model and try to identify its behavior. So in figure 2, we are looking at the evolution of the reference model. In this model, we have cratonic coverage of 46%, and that value is reached by 300 million years. Initially, we have higher temperature profile in figure A, and the cratonic coverage is small. Therefore, the model is dominated with the basaltic crustal drifts. One of my previous studies suggests that these drifts are suitable for TTG crust formation in the early Earth. the craton coverage eventually increases, and you can see cratonic sizes are getting bigger. And when the craton size increases, most of the downwelling basaltic crustal drips are trying to converge towards the craton boundary. When the mantle gets cooler, the mantle convective cell sizes also increases, and that supports this convergence. So therefore, in figure 2c, we can see the most of the drips are converge in the craton boundary, and some of them replicate subduction or features of the subduction, but these subduction events are not sustained for long, and they are mostly episodic. So in the fourth slide, we are looking at the mantle thermal evolution and the Nusselt number variation for various cratonic coverages. So in figure 3a, it shows the mantle cooling rates. So the black color curve basically represents a model that does not have any craton. So it evolved freely and reach a cooler value faster. But when you increase the cratonic coverage from 0 to 78%, you can see the thermal stabilities reach a higher value, and ultimately the model transit towards a stagnant lit condition at 78% of cratonic coverage. In the figure 3b also, we can see in the Nusselt number distribution, this red color curve basically represents the 78% of cratonic coverage, and these spikes represents lithospheric overturns in the model, and the model with 78% of cratonic coverage has lithospheric overturns up to 300 million years, and afterwards it gets flattened and reach the stagnant lit like conditions. So these are our preliminary results. And in the fifth slide, I'm comparing two models. One has relatively lower cratonic coverage, and the other has relatively higher cratonic coverage. The model has lower cratonic coverage, reach the low temperatures faster, and also we can see the subduction like features are more prominent in this figure 4a models. But when you go to figure 4b, figure 4d models, we can see cratonic coverage is large and the oceanic lithospheric region is very small. Therefore, we don't see any subduction like features in the figure 4d. Instead, it has some kind of a motion in the oceanic lithosphere, but it's very low velocity profile. And also the highest heat flow in the model is observed through this oceanic lithospheric region. The reason for not having the subduction event in this model is the oceanic lithospheric region cannot reach a sufficient thickness as it detaches from the model surface. So these are the major variations based on the cratonic coverage. And also in figure 4b and c, we are looking at the surface heat flow profiles and the velocity profiles of the figure 4a subduction events, and these patterns are compatible with the present oceanic plate features. Yeah, those are the preliminary results models. And here in the last slide, I am going to showing the summary of this poster. And if you have any questions or queries or suggestions to improve this research, please contact me through chat function in the poster session, or contact me through email. I highly appreciate your time spent on this poster. Thank you.